Hey everybody, I realized this morning that I forgot to upload a lesson yesterday. I was off on my days, and so congratulations on having a spare day. I didn't feel bad though, because I think that you guys have been working really hard as we've gone along. I'm uploading this now. We'll be going on an A-day schedule instead of a B-day schedule. And I've noticed that several people are a few days behind me in the lessons, and that's okay. We are going to be coming up on a test pretty soon, just so you're aware. But from your interactives that we did last time, what I was hoping that you would look at is how it's different when you add together resistors in parallel versus in series. And so you may or may not have discovered the equations as you've gone through the interactive, but we'll start with the resistors in series. Your total resistance, if you have a set of resistors added together, is very simply you just add those resistors together. Parallel will work different. I think you hopefully saw that in the interactive. But there we go. It really is going to be this simple as you go through your series circuits. I think the biggest difficulty you'll have is going to be keeping straight which one's which. Alright, so I get... Make sure I added that together right on my other screen. I get that this is what we have when we add together our resistors that are in series. And again, same thing. Here's another circuit where your resistors are in series, and your total resistance in series, when your resistors are in series, is just going to be to add them together. Okay, really is that easy. Now, I will spend a little more time with adding them together when they're in parallel because the equation looks different and it uses fractions. But I'll go through more than 2 examples on those just so you are ready for it. Okay, so like I said, the equation for resistors in parallel does involve fractions. The equation looks like this. Since there are only 2 resistors here, I'm just going to put 2 in the equation. For the example down below where there are 3 resistors, I would have 3 fractions on the right-hand side of the equation. So you're going to have to deal with fraction rules. Don't stress about this because I let you use calculators. But what we would do is we would plug in our numbers. And if I wanted to not use a calculator, I would need a common denominator. If I multiply top and bottom on the second one by 3, then I get 1 over 27 plus 3 over 27. And I could add them together to get 4 27ths and get them down to a single fraction, which is what you want, or a single term. I'm also going to be okay if you pull out a calculator. And then let's show you, going back to the original problem, you can type in 1 divided by 27 plus 1 divided by 9 and use this number instead. It's not quite as nice because it's a repeating decimal. It's nicer to see what that is as a fraction, which of course would be 4 27ths. But I am okay with you using it and getting your approximation. So let's show you first with how I would use the fraction version, and then I'll show you how to use the decimal version. So I want to find what my total resistance is. When you have it set up with a fraction equals a fraction, then you can cross multiply, remember. So it means that I'm going to take 27, cross those out, multiply by 27 upstairs over here too. And then I want to get rid of the RT on the bottom, so I multiply by RT on the top over 1 so that they cancel, and RT on the top here so they cancel. And after I look at what's left, I'm left with 27 times 1 divided by 1 is still 27, equals 4 RT. I take that and I divide by 4, and I get that RT equals 27/4, which is going to be the same thing actually, let's undo that. Which will be the same thing as, nope, 6 point, I think it said 75. Yep, 6.75. All right, so that's the total number of ohms that we have. What that means is I could take out all of my resistors that I had in this problem, or both of my resistors, and I could put in a single resistor that was 6.75 ohms, and I would have the same results. This is what we're going to practice with today. So if I were to do this problem, I'm going to do it up here instead. If I was going to use the decimal instead, I personally would use, I would say probably a very, very minimum of 4 decimal places. I think probably 6 decimal places would be even better. So that's what I'm going to put down here. And then you do the same thing, but you make it into a fraction. And we're going to cross multiply. So when we do that, we end up with 1 is equal to 0.148148 times RT. And then, looks like I didn't give myself quite enough room. And then we're going to divide by the stuff that's not RT. 0.148148 divided by 0.148148. And we should get the same thing that we got earlier, although we might be off by a decimal depending on how many decimals we used. 0.148148. And yeah, so the decimals, you can see they are off a little bit because I didn't use all of the decimals involved in the original answer, but still good enough. 6.75 ohms. So because I know you guys are going to use calculators, I'm going to use calculators for the rest of my examples. Here for our next one, we know that our total resistance is going to equal 1 over each of the resistors that is present. And so go right ahead. I am okay with you using a calculator. Just make sure when you type in your fractions that you do keep these fractions separate. Like, for example, here, when you're not careful, they'll end up trying to put the fractions into one fraction, which you don't want. So you have to go hit the right key to make sure you are starting a new line outside of the fraction. Alright, so here I get my total resistance is going to be 0.14590909. And the more decimals you give yourself here, the closer you'll be to the real answer later. Once you've got this in a single number, time to cross multiply. So 1 times 1 is 1. 0.14590909 times RT is 1.14590909 RT. Divide by the stuff that is not RT. And do it on the other side. 1.45, forgot the 1. 90909. And so with the calculator, hopefully it's not going to be too awful for you. I know that's one thing that I do wish that elementary school teachers would spend more time with fractions, because I don't think they always remember necessarily how much we use fractions when we get to high school and especially in college, but they do come up all the time. Alright, so the equivalent for that circuit would be a 6.85 ohm circuit. I could take all three of these resistors out and put in a resistor of this size. Now, why would you want to put in perhaps these resistors when we could put in a resistor of this size? The honest truth is, you're not going to find a resistor that's 6.85 ohms in strength. You would want to create, if you have a specific resistance you need for your circuit, you would want to create it with the resistors that you have. Alright, so let's do a couple more examples. Okay, so let's say that this is the example that we are dealing with. We're going to have 1 over our total resistance, and this is, again, anytime your resistors are in parallel to each other. This is the equation that you're going to use. And you just add on as many terms as you have in your circuit. If I had 60 things in parallel, I'd add 60 things in the equation. I won't give you one that big, though. Some of you got nervous just now, and I know who those people were, too. Alright, so using my calculator, I get what those fractions equal together. 0.2857575. And remember, well, actually, you know what? I'm not going to cross multiply necessarily right now. What I'm going to do is the same thing exactly, but I'm going to just multiply by RT here and multiply by RT here and get 1 equals my big long decimal. And then I divide by the stuff again that's not RT. One divided by my number. And there I go. That circuit was going to be the same thing as basically 35 ohms. So putting all of these together would be the same thing as using a circuit with 35 ohms instead. And again, like I said, not every size resistor is actually produced, so this is something that's very, very common to use in circuitry, because you do need specific resistances in certain places. So our next step is we're going to combine this with Ohm's law, but I'm going to do that in the next time's lesson. We are only going to spend another day or two on circuits, and then take our test, and then move on. So if you have any questions, let me know. I hope you're doing well. If you're doing this over the weekend, have a great, great weekend. I hope you're having a great weekend, and let me know if you need anything.